So tonight we have Dr. Kerry Emanuel, MIT professor, who is going to share his knowledge with us about hurricanes and the effects of climate change on hurricanes. So I'm going to hand it off to Kerry, and he's going to share his presentation with us.
Yeah, well, thank you very much, Suzanne. It's a pleasure to be with all of you tonight. I only wish I could be with you in person. I'm in fact in Maine myself, up in New Harbor. And so what I thought I would do is talk to you a little bit about the subject of hurricanes in Maine, telling you a little bit about the history of hurricanes and addressing the question, are we ever going to see one again? Or more generally, what can we expect climate change to do to the character and frequency of hurricanes up here in Maine? So I'll go right to my presentation now, if I can find it. There it is. And I hope everybody can see that. So the title is Hurricanes in Maine, Past, Present, and Future. I'm going to start out talking about some famous, or you might say infamous, hurricanes up here. Not so many recently, but boy, back in the 50s, we really got slammed. In fact, I'm going to start with one of the most famous New England storms, Hurricane Carol of August and September 1954. It really roared into Maine on the last day of August and exited the state in the early morning hours of the 1st of September. Oh, I should say about this chart, this is the path of the center of Carol. And if you look at that color scale on the bottom, that's the peak wind speed anywhere in the storm with time. The numbers that you see along the path are just dates in August and September. I'm going to show you a bunch of charts that look like this. So Carol was responsible for 3 deaths here in Maine, but 65 deaths and 1,000 injuries in New England in general. It did $10 million in damages at the time, which translates to about $250 million today. So it was a very expensive event. And throughout New England, it was, in today's dollars, a $12.5 billion event. So we can get some very damaging storms up here. The peak wind gusts recorded on the coast of Maine were about 78 miles per hour, so easily hurricane force. 2¼ inches of rain in places. It's not that much, but we'll see that it had a role in setting the stage for yet another hurricane disaster just a couple of weeks later. Power was lost in all of Greater Portland. Most lobster fishermen in Maine reported damage to their gear, and 3/4 of the whole Maine apple crop was destroyed. Here are some photographs. The left one is of a ship that was washed up in Falmouth. And on the right, you see a tree damage, beautiful elm trees falling down in Portland. Not even the governor's mansion up in Augusta was spared. That mansion you can see behind the fallen tree on the left there. This is a scene from a clip that you can find online I don't know where in Maine this is actually, but it was during Carol. And here is looking southwest from Ocean Point in Booth Bay during the storm. So it's a really gigantic seas and a lot of coastal flooding. Down in Boston, the 148-year-old steeple of the Old North Church fell down in Carol. So you see that this was, at least measured by that, a fairly rare event. Otherwise, a previous storm might have taken that steeple down. Now, just a couple of weeks later, the same year, in September of 1954, was Hurricane Edna. And here's a track of Edna. It came up a little bit further to the east, and it passed just offshore of most of the coast of Maine and did most of its damage here on the 11th and 12th of September. There were 8 deaths in Maine from this storm and about the same amount of damage, $240 million in more or less today's dollars, and similarly high winds, peak gusts of 70 miles per hour in Maine, but much more rain. So we had rainfall totals as high as 7.5 inches during the storm, and that came on top of the rain from Carol, and that caused a lot of flooding. So the Androscoggin and Kennebec rivers both reached well above normal levels. causing flooding and washing out roads, and President Eisenhower declared Maine a disaster area. That doesn't happen very often up here. Here is a scene from Southwest Harbor during the storm. And here is Memorial Highway in Yarmouth, which is today Route 9, okay? And if you've ever been down Route 9 Yarmouth, you know that there's a bridge there today. It's well over the level of the river. So that river was really, really quite high above normal. And there was a lot of damage to a dam up in Limestone, Maine. You can see the water pouring over the dam there. I remember this because they rebuilt it, but this is a drive-in movie theater in Rockport, completely demolished by Edna. They rebuilt it later, but they later tore it down for financial reasons. It inspired a lot of interesting writing and art. The famous story by E.B. White in the New Yorker of September 25th, 1954. He was in North Brooklyn, Maine, and wrote a beautiful article. You can find it online, or if you can't, write me, email me, and I'll send it to you. I'm going to read a short quotation from it. At 8:44 p.m., the power failed. The house went dark, and it was a whole lot easier to see Edna. In almost no time, the storm grew to its greatest height. The wind, which was northwest by this time, chased black clouds across the ailing moon. The woods to the south of us bent low, as though the trees prayed for salvation. In front of the house, a large branch of the biggest balm of Gilead tree snapped and crashed down across the driveway, closing it off. On the north side, an apple tree split clean up the middle, and for half an hour or so, Edna held us in her full embrace. Nice article. Down in Massachusetts, Thomas Hart Benton painted a scene of the hurricane in his inimicable style. I love his work in general. It's a particularly nice painting that I didn't know about until a few years ago. It depicts Hurricane Edna affecting a small village, fishing village in Martha's Vineyard. This is another storm that Donna, that came screeching along. It didn't do so much damage up in Maine, but 20 to 40% of the apple crop was destroyed. And this is Daisy of September through October 1962. You see, this is quite an active period, the 50s and the 60s. It was pretty far offshore, but it nevertheless killed people in Maine. It was a very large circulation. So 2 deaths from falling branches in Thomaston and Rockland. 9.5 inches of rain fell in Portland. That was an all-time record that held up until Hurricane Bob of 1991, about which more in due course. Wind gusts to 70 miles per hour in coastal Maine, even though it was far offshore. Now this, I'm having a little bit of a technical problem because the way this is set up, I'm just going to quickly. Oh yes, the way this is set up, I can't see the title of my own slide, so I'm going to have to sometimes bounce back and forth. But this is Gerda, which made landfall near Eastport as a Category 2 hurricane. Probably the strongest hurricane technically to strike the Maine coast in recorded history, but most of the high winds and damage, I mean, it's a little bit of a technicality. You notice that the center of it goes over the extreme eastern port of Maine, but all the high winds were in Canada, Nova Scotia, mostly. And so there wasn't much damage in Maine. Technically, it was the strongest storm in Maine, sort of squeezed in under a technicality. Now this is Hurricane Kerry of August through September, 1972. And it wasn't a very strong storm, but there were 2 deaths here from high surf. Now, after that, we entered a long hurricane drought. And it wasn't just Maine. The whole North Atlantic went quiet. And what I'm showing you here is a record of the frequency of major hurricanes over this whole period of time in the North Atlantic. Now, the interesting thing about this is that this is not actually drawn from actual recorded records of hurricanes, but from a simulation of hurricanes made given the observed large-scale properties of the climate. And I'll tell you a little bit more about that later. But it starts in 1851 and it goes to about 2010. The green line is just a smooth rendition of this. And this is the frequency of category 3 to 5 hurricanes in the whole Atlantic. And you notice that starting in the late 50s, actually around the 60s, there was a big drop off. It kind of reached a minimum in the 80s and the 90s, and then it came roaring back in the 2000s. And a lot of scientists have ascribed this to a natural oscillation, but the current thinking, based upon some really neat research, is that this hurricane drought, remarkably enough, was a man-made drought. Not to do with greenhouse gases, but to do with sulfur pollution from burning land and from burning fossil fuels. Mostly pollution stemming, in this case, from Northern Europe. It gets swept down over the Sahel, causing a drought there, and then great big dust storms, of which, by the way, one is in progress right now as we speak, a huge dust storm going out over the Atlantic. That has the effect of cooling the Atlantic and dousing the hurricanes. So Maine also had a hurricane drought during this period. That, by the way, that blue line is a flipped upside down representation of European sulfur emissions. And you can see how well it sort of fits that, if you fits that curve. But that drought was interrupted by a rather spectacular storm. Some of you remember Hurricane Bob of August of 1991. It's the last time we had a really big hurricane up here in Maine. Here's a satellite picture of it. By then, of course, we had really great satellite images. And you can see the sort of pinpoint eye in the center of the storm. I'm going to use my cursor. I don't know if you can see that cursor, but it's right here, surrounded by the eye wall, which is where all the strongest rain occurs and heavy wind. Now, New England hurricanes are kind of special. Hurricanes can't survive over the cold water we have here all the way down till you get to the north wall of the Gulf Stream. So all hurricanes coming here are technically in their death throes. But at the same time, they can start interacting with non-tropical weather systems, ordinary weather systems that we experience all the time here. And that can kind of revive these storms a bit. We have a technical term called extratropical transition to this. When they get up here, the only time that we can get really damaging storms, if they are like Bob, moving very fast toward the north. So they don't have much time to die before they get here, quite literally. This also means that almost always the strongest winds that we have are from the south. So any kind of south or southeast exposure in Maine is a bad deal for hurricanes. This is the track of Bob. It made landfall twice. This is August of 1991. Once in Rhode Island and crossing Massachusetts, and then a second landfall in mid-coast Maine. So its second landfall was in fact near Rockland. It was one of the costliest hurricanes to ever strike New England, $2.75 billion in 2019 dollars. 3 deaths in Portland, gusts to 70 miles per hour there, and 92 miles per hour in Wiscasset. It was really quite large for a New England storm. 8 inches of rain at Portland, and 170,000 residents of Maine lost power, some for more than a week. There was an unconfirmed tornado in St. Albans. Hurricanes often breed small tornadoes, but they can be very damaging. And there was a 2 to 3 foot storm surge, which is like a mini tsunami, same kind of physics actually, along the coast. River flooding washed out 5 bridges and roads across southwestern Maine. Now, what we'd really like to know is how risky is living in Maine? How much at risk are we from hurricanes up here? And the problem is that it's really hard to tell. And we're beginning to bring more scientific methods into this. And I want to tell you a little bit about that story. This is probably the most technical chart I'm going to show you. And if I don't get the point across, feel free to unmute and tell me off. I don't mind at all. What you're seeing here on the left is something called a probability curve. And it's the probability of damage from hurricanes. This is not for Maine. I'm going to get there later. This is for a completely different part of the world, but I'm just using this to make a point. So on the left-hand axis is the probability, and on the bottom axis is the damage. And those numbers 6 mean 10 to the 6 or a million, 10 to the 9th is a billion, so 9 means a billion, 12 means a trillion, okay? So there's sort of a peak, the average storm, if you will, the ordinary run-of-the-mill storm for this particular portfolio property, and I think it's across all the US, does about $100 million in damage. That's 10 to the 8th if you look at the bottom axis. And it's not very likely you're going to see storms that cause much less than that, and it's not very likely you're going to see storms that cause much more than that. There's not too many storms at $10 billion, which is 10 to the 10th, or 10 on the bottom axis. Now, the blue curve is for our current climate, and the green curve is for a future climate. I won't say exactly what I mean by that yet, but this, again, is just for illustration. So those are the probabilities. Now, what we can do is take the same data exactly and express it a little bit differently. We're going to multiply the probability by the damage itself. And then we get this curve. All right, so this is two curves, and the area between those curves and the bottom axis is proportional to the total amount of damage across all hurricanes over a very long period of time. And you can see that the green curve is now way, way above the blue curve. It's almost triple the area. And the thing that did it was that tiny little bump you see in the left-hand chart here, where the future future likelihood of really, really damaging storms, you know, billion, 10 or $100 billion storms, goes up a little bit, and that has really big consequences. And what this illustrates is that what we're really worried about is not the run-of-the-mill hurricane. It doesn't do a lot of damage. There are lots of run-of-the-mill hurricanes in Maine I didn't even tell you about, all right? It's the big ones that we worry about. They're the ones that do damage. Now, the heart of the problem is actually anthropological, not meteorological. It has to do with the way we live. And the bottom line is, across the whole world, societies are usually pretty well adapted to frequent events, and frequent means about more than once in 100 years. That makes perfect sense. We build our houses so that your everyday windstorm doesn't blow them down, or a windstorm that might occur every decade doesn't blow them down, all right? Or any other kind of catastrophe, okay? Earthquakes in earthquake-prone regions, little earthquakes you have every 10 years or so aren't usually going to do a lot of damage. But the flip side is that the rare events, the ones that are about less than 100 years, you might ask yourself, what's so magic about 100 years? It's a few human generations. If something bad happened to you, you remember it. If something bad happened to your parents, they probably told you about it. Maybe your grandparents told you about something awful that happened in their day. Much beyond that, you're not going to hear about it. Okay, that's just sort of social memory, if you want. So the rare ones, the ones that are less than 100 years, are the ones we worry about. But if you want to know how often they occur, you need about 1,000 years of records, right? You need to have a lot of time to estimate a 1 in 100 year event. But we don't have 1,000 years of records on almost anything, certainly not in Maine. Well, almost nowhere I can think of do we have 1,000 years. So this is the problem with using historical data to estimate risk. It's even worse than that now because the climate's changing and history is no longer necessarily a very good guide to the future. So at MIT, we've developed a different approach to this, and we use physics, not just history, to estimate hurricane risk. So how do we do that? Well, we're going to start with a global climate analyses that may go back 100 years or more. Okay, this is just from all the data around the world. It's not a hurricane climatology, it's a global climatology of weather patterns, of jet streams and so forth. And those analyses don't generally have hurricanes in them because they're too small to really, they just weren't recorded. So what we do is we embed in those analyses very specialized hurricane models that were developed really to forecast hurricanes in real time. And in fact, they're still being used that way. And they're very high resolution, very fast. And we can embed that either in this climate analysis data or in the output or on the time evolving output of climate models. And the model I'm going to show you here, we've used for about 16 years to forecast real hurricanes in real time. So what we do is kind of interesting scientifically. We take this large-scale climate state with all the large-scale weather patterns, the winds, the pressures, and so forth, and we seed them with a very large number of weak proto-cyclones, pre-cyclones. And the next step is to find out where these seedlings go. And that's pretty easy because hurricanes just sort of move with a large scale flow in which they're embedded. And then we run this specialized model along each hurricane track to forecast how strong or weak the hurricane gets. And we note how many of these seedlings get to at least tropical storm strength. Now, it turns out that literally about 99.9%, so a little bit more than that actually, of these seedlings just die because you put them in a bad environment that they didn't want to grow. So you can think of this as kind of a natural selection technique. Only the seeds you put in a relatively healthy environment are going to grow. So, but we can afford to do tens or hundreds of thousands of survivors, okay, because the method's very fast. So we can generate, if we want, 100,000 events. Now, does it work? That's the big question. You can dream up these things. Well, we didn't actually think it would work, but we're surprised that it works pretty well. So here is an example of a mere 1,000 hurricane tracks all over the world. I don't know if you've seen charts like this for real storms. It's pretty realistic. The little circles are where they start, and then the arrows show sort of where they end, and the colors are proportional to how strong they are. And they do sort of capture the general features of the climatology of hurricanes. By the way, most hurricanes in the world occur in the western North Pacific Ocean, the Indian Ocean, and the South Pacific. There are only 10% of the world's storms occur in the Atlantic, but they get 98% of the press. And this just simply shows in blue the peak wind speed recorded in each storm over its lifetime from a little over 210 actual storms between 1990 and 2005, and from these synthetic storms I just described, a somewhat larger number. So the way to read this is the number of storms that exceed the wind speed you see on the bottom axis. So this declines because as you get to higher wind speeds, there are fewer and fewer storms. But if you compare the blue and red bars, you're comparing historical events to the events that we got from this technique I just described. This shows the number of storms per month. So we go from January at the lower left to December at the lower right, and the y-axis, the vertical axis, is the number of storms per month. The blue dots are from history, and the red curve is from the synthetic technique. And we can do things like calculate how often storms of a given wind speed occur. So this is for all of New England. If you look at the left-hand axis, it's 100 knots. If you read over to the right and then down, we see 100-knot wind occurs in New England once every 40 or 50 years, okay? The green dots are from history. The blue dots are from the method I just described. But we can go and look at much rarer events with the method I described because we can generate a whole lot more of them than history has done for us. Now for this talk, I use this technique to generate 1,800 tropical cyclones that affected the coast of Maine. All we do is throw out all the ones that don't, basically, as we're going along. It's a filter. And this is from a climate analysis. It's not from a climate model. This is from a historical climate analysis. And these are the tracks, and the colors show the wind speed. These are the 50 most damaging of those 1,800 storms. So I'm showing you the top dogs here crossing the coast of Maine. And you can see, not surprisingly, they all come out of the south. Some of them come out of the south-southwest, that is, they're over land, but they're moving so fast that they're still very damaging. Some of them come from the southeast. Most of them come pretty much from the south. And you can see where they started, anywhere from off the coast of Africa to a very few cases that actually start out in the Gulf of Mexico. Most of them are in the Caribbean, all the way over to Africa. This is a 500-year event. Okay, this is again a synthetic storm. This is the kind of storm that's so violent that in the current climate you would expect it on average once every 500 years. What that actually means is that every single year there's a 1 in 500 chance of getting a storm of this magnitude. Again, you're seeing dates in September. This comes roaring out of the south. And see, if we look at, oh yes, I wanted to show you this. This is the winds associated with that event. So we're looking at a map of New England. You can see Maine in the center. The black curve is the curve along which the center of that violent hurricane passed. And then the shading shows the peak wind experienced sometime during that event for every point on this map. So you can see to the right of the track of the storm, there are winds over 100 knots, nautical miles per hour. And along the coast, you see some winds between 90 and 100 knots. But then, as is always the case with hurricanes, the winds fall off pretty quickly inland. But notice that even in Augusta, you're getting 60 knots, you know, basically marginal hurricane force winds from this event. Now we look at all of these tracks affecting mid-coast Maine. And what we see here is kind of what you would use to estimate your chances. It's something called the exceedance frequency of storms. And then on the bottom axis is wind speed. So hurricanes have winds by definition over 64 knots. So let's look at 64 knots here. The red line is from all these synthetic events, and it says that the exceedance frequency is 0.05. That is, every year you have a 5% chance, and we would call that a 20-year event. Okay, the 21, you know, on average, every 20 years or so, you would get a hurricane somewhere on the coast of Maine by this reckoning. The blue dots are what you would estimate from the very small, actually only 14 historical hurricanes that we have. And there just aren't very many. And the blue shading gives you some idea of the uncertainty that arises from the fact that history is there's so few storms in history. So if that red curve falls within the blue shading, it's consistent with history, but that doesn't tell you very much because there's so little history of hurricanes in Maine. This chart shows something called the power dissipation. It's a measure of how destructive winds are for storms crossing the coast of Maine. And I've sort of divided into 4 segments, although you can't easily tell the difference between light and dark red here. What this shows is that the more violent storms occur further north and east along the coast, and that the southern Maine coast in New Hampshire is really protected by Massachusetts and land masses further south from the most violent storms. And the further down east you go, the greater risk you have of very destructive events because they come roaring up the Gulf of Maine without going over it. This is a track of another synthetic storm that we generate from the current climate. But this is showing you the track, and you'll notice the wind speeds are really weak in this event, so why am I showing this to you? This wouldn't have caused much wind damage at all, 40 knots. This turned out to be to cause the 500-year rainstorm in Maine. That is, this storm rained like hell, okay? It did so because just after it made landfall, it kind of stalled. You can't really see that easily on this chart. What this shows is the accumulated rainfall over the whole life of this event in Maine. And so you can see there's a whole region in central and southern Maine that got 8 inches or more of rain, which, if you remember, was what Portland got, for example, during Hurricane Bob. So, but this is a very rare event. Now I want to turn to the subject of climate change and how does it affect hurricanes. And I'm going to give you a 1-minute tutorial on the subject. And you might be surprised by how I introduce this, but I kind of like this character. This is Svante Arrhenius. He was a Swedish chemist who lived at the end of the 19th century, early 20th century. Very bright guy, won the Nobel Prize in chemistry. And he dabbled in other things. And he was the first to worry that the burning of fossil fuels would raise the carbon dioxide content of the atmosphere and cause the temperature to go up. And he published a paper in 1906 that said if you double carbon dioxide, it's going to go up about 4 degrees. And that's remarkable because the most modern estimates of what that number should be is somewhere between 1.5 and 4.5 degrees. So all we've done in the 100 and some odd years since Arrhenius has put error bars on his estimate. Now, we can actually test, by the way, look at this guy. He doesn't look too happy. And I like to say that Arrhenius set the standard for the demeanor of climate scientists ever since. Let's look at Arrhenius's prediction. So this is a chart that's started in Arrhenius's day around 1880 and goes up to the present, more or less. The blue curve is is a measure of the carbon dioxide content. For those of you who have a technical background, it's actually the logarithm of the CO2, which is proportional to the radiative forcing. And the red let me back up. The blue curve is the temperature that would be predicted based on that carbon dioxide concentration from Arrhenius's theory, if you will. The red is what actually happened to the temperature. And I'd say that, there are lots of wiggles and all kinds of other things influence global temperature, weather, and so forth. Generally speaking, Arrhenius made a pretty good prediction. And, beyond this, there is just so much evidence now that we're changing the climate. It's just not disputed within the scientific community anymore. What we're all worried about is how bad is it going to be going forward. And that's where we're not doing such a great job. So what you see on this chart is an estimate of how much the Earth's surface would warm if you doubled carbon dioxide. And that black line at 4 degrees centigrade is Arrhenius's prediction. The blue dots are predictions from a whole suite of different global climate models. These are really complicated algorithms that are used to estimate the response of climate to a change in forcing. And you can see they scatter from about 2 degrees to about 4.5 degrees, okay, with sort of a mean a little bit more than 3 degrees. The orange dots are the same thing, but for the current generation of climate models. We try to improve them as they go on, and the estimate has increased a little bit, but it's sort of still in this range. But these are really broad ranges, and it shows you that there's no hiding the fact, and nobody attempts to hide the fact. There's a lot of uncertainty in this. And if we end up with 2 degrees, it's still going to be pretty serious. If we end up with 5 degrees, I don't even think I want to think about that, to be honest with you. But let's go to the topic at hand. How is this going to affect hurricanes? Well, we can take this technique and just as easily drive it with climate models as climate observations. It's the same thing, basically, technically, to do this. We're going to apply it to 5 global climate models of that earlier generation I showed on the previous map. And we're going to run 1,000 tracks over Maine for each model for each of 2 time periods, the end of the 20th century, 1981 to 2000, and the end of this century. Whoops, I see a typo. That should be 2081 to 2100. Sorry about that. Last 20 years of this century, assuming that we don't do anything to curb emissions of greenhouse gases. And this is what happens. So this is a chart where, again, on the left axis, you have the frequency of events, and on the bottom axis, the wind speed. So if you look at the blue curve and the shading going along with it represents the last 20 years of the last century. So more or less the current climate, although we're well out of that period now. And by that reckoning, you should see hurricane force winds every 500 years in that climate, okay? On the coast of Maine, 64 knots or more. The blue shading represents an uncertainty in this estimate amongst the 5 models that we used. The red is exactly the same thing, but it's for the end of this century. And you can see that rather than having it once every 500 years, we have it once every 130 or 140 years or so, okay? And with some uncertainty. So it looks like climate change is increasing the probability of having a hurricane in Maine, all right? That's true, not true everywhere, by the way. When we run this technique, there are places, I heard Suzanne talk about the next talk being about Fiji. As it happens, we did a study for Fiji. We do studies for a lot of areas. Fiji, the risk actually goes down because of global warming. So it's not uniform around the world at all. Maine, unfortunately, it looks like it's going up. This is exactly the same thing, but it's for rain. And we're looking specifically in this case, not at the whole coast, but at Portland. Just chose that arbitrarily. And the storm total rainfall is on the bottom axis and the frequency on the left-hand axis. And so you can see that in the climate of the late 20th century, having 10 inches from a hurricane in Portland was extremely unlikely. Once every 3,500 years or so. Forget about it, it's just not going to happen. But in the climate of the last 20 years of this century, it goes up to about 100 years. So it's still rare, but you're going to see it every once in a while. There's a huge difference between those two curves. So there's much more effect on rain than on wind. Here is the track of the storm at the end of this century, the 500-year storm, the storm you expect to see with a probability of 1 in 500 every year, a very rare event. This is a real doozy of a hurricane. It comes roaring up in October, okay, and makes landfall with winds of 110 knots or so, right in mid-coast Maine. This is just one event. Here is, again, the wind swath associated with that. The storm center moves up along the black line, and the shading shows the wind speed, the color scales on the right. So you're seeing winds of 110, maybe even 120 knots along the Maine coast, east of Penobscot Bay for this particular event. And here's the same kind of curve that I showed you. This is for one model, one of the models. This is for the 20th century. It shows an estimate of damage. Again, not much along the southern Maine coast, south of Portland, getting worse as you go down east. And then for the end of the same color scale, for the end of the 21st century, it doesn't change much south of Portland. But boy, if you go east, things get really bad. So, you know, if you're living in southern Maine, the hurricane risk isn't going to change very much, except for the rain. And so if you're susceptible to river flooding, that's something to worry about for sure, but wind, not so much. Down east, you're going to get it in the ear both ways. Now, this is a storm that produced the most rain, well, not the most rain, but it's a 500-year event for rain from this set. And here it is. It happens in the year 2096. And you can see there are parts along the Maine coast that get 15 inches of rain. Okay, that's a heck of a lot of rain. You get really, really bad flooding of the rivers for that. Now, further south, of course, they can get a lot more rain than that, like happened in Houston. But here in Maine, you know, it's colder. We don't get so much rain, but enough to cause problems. So let me wrap this up so that we have time for questions. Try to summarize this. Maine is mostly protected from hurricanes by the cold water north of the Gulf Stream, between the Gulf Stream and Cape Cod and the islands. And it's just the only way you can get a strong storm up here is if it's moving too fast to have wound down very much by the time it gets to Maine. So Maine has experienced several low category hurricanes. They're mostly category 1, maybe category 2. and of course tropical storms, and they've taken lives and caused a lot of damage, particularly back in the 50s and 60s. Hurricane risk increases, at least the risk of high winds increase as you go down east along the coast. It may not be intuitive because of course you think, well, you're going north, it's getting colder, and you are, but that's completely outweighed by the fact that you're not shielded from land to our south if you're further down east along our coast. If we don't do anything to curb greenhouse gases, projections suggest a modest increase in the frequency of severity hurricanes in Maine by the end of the century. Most of that increase occurs down east. And the thing that concerns me more than anything else in Maine is the large projected increases in hurricane rain. Rain, by the way, kills a lot more people than wind all around the world in hurricanes. They're advertised as windstorms, and they are, but the rain turns out to be killer. And so we're concerned that this could lead to substantially elevated. If you have questions for me, please do type them under the, I can start to see some under the chat. So from John, did your model results take into account the unusual warming of the Gulf of Maine that's been measured lately? Very nice question. No, it didn't. We use climate data for a period of time that was mostly before that warming. We could now, that some time has passed, use climate data from the last 10 years or so and rerun it and see what that does. My guess is it does something a little, not very much, and I'll tell you why. The warming is pretty spectacular, but it's actually not covering a very large area. The Gulf of Maine has warmed a lot more than most of the Atlantic. I think some of you know that. But it's, you know, it's maybe 100 kilometers offshore, and then things sort of go back. There's a little bit of warming. I guess this is not, it's not enough warm water to have an effect. Maybe more on the rain. So an interesting question, and if I have time, I'll try to look into it and see if we see a big effect from that. From Aaron, if you don't mind me using your first name. Thoughts on this year's hurricane season? Well, my colleagues who predict these things say we're going to have a doozy of a hurricane season. Let me tell you how I feel about that. Historically, the people who have made those forecasts have shown a little bit of skill. They're often wrong, but they're right more than they're wrong. But it's a skill in a quantity that I would argue nobody really cares about. How many people, unless you're just fascinated with hurricanes or in the gambling mode, really care how many hurricanes occur in the Atlantic? What you care about are the dangerous landfalling hurricanes, and nobody pretends to be able to predict how many of those there will be. They're not that strongly correlated with the total number. Let me give you a concrete example. Hurricane Andrew occurred in 1992 in South Florida, and at the time it occurred, it was the worst insurance disaster in the whole history of the US. It put many insurance companies under. A very violent storm. It occurred in one of the quietest years we've ever seen in the Atlantic. Very few storms. The A storm didn't occur until the end of August. We've already had 4 named storms, and it's just the end of June. It was a quiet El Nino year, and I think that making a seasonal forecast has the unintended consequence of either getting people overly worried or letting their guard down, when in fact you can't really predict the things that matter to people. From Sheila, how much of a role does machine learning play in the climate models that you've mentioned? How does that compare to everyday forecasting? Well, that's a really good question, Sheila. Right at the moment, almost none, but that's changing fast. Lots and lots of people, colleagues of mine, not me myself, but colleagues of mine, have been starting to apply machine learning techniques to climate models to improve them and to help us understand their output. And you ask also, how does that compare to everyday forecasting? Well, forecast models have a big advantage of climate models, both in their raw output and when it comes to applying machine learning to the output. That is, you know what actually happened, okay? With climate models, you don't. You have to wait too long. We can test a weather forecast model arguably twice a day and have been doing that since we started doing numerical weather prediction in the 1950s. It's been a huge success, by the way, numerical weather prediction. And machine learning is being applied not so much to the models themselves as to the interpretation of their output, relating what the models are telling you at grid lattice points to what actually happens at individual points on land, for example. You asked which satellite data sets we're using. Well, for the study that I showed you, we aren't using any actually, except that the climate reanalyses that we use to drive this hurricane model are ingesting all kinds of different satellite data and everything else you can think of. Weather balloons, commercial aircraft. By the way, as you probably are aware, the commercial aircraft traffic is down 95% because of COVID around the world. And a side effect of that is we're getting a lot less data into our models. And so we're actually trying to detect to see how degraded our weather forecasts have become because of missing that data. From Nick, would storm surges increase more with wind speed or wind field? In other words, are our low-lying coastal communities, even in southern Maine, at higher risk of weaker but wider hurricanes? You know, that's a really terrific question, and it's something we worry about. So let me try to give you an honest answer. The surge is the second biggest killer in a hurricane. I mentioned freshwater flooding. Saltwater flooding from surges is a terrible source of loss of life and damage in storms. Now, what dictates how big a surge is? Basically, it's the speed of the wind and the duration of the wind and the fetch of the wind over the water. The duration depends on the size of the storm and how fast it's moving, and the fetch also depends on the size of the storm. So to give you an example of how important the size of the storm is, Hurricane Sandy caused the worst, by far the worst flooding of Manhattan since the tide gauge went in 1923. But it wasn't Hurricane Sandy, it was Tropical Storm Sandy. The peak winds in that were completely unremarkable, but its circulation was huge. So that means that if we want to understand how hurricane hazard changes going forward, we have to not just predict the paths of storms and their wind speeds and their rainfall, we have to predict how big they are. And we don't know how to do that yet. That is, we don't fully understand what controls the size of hurricanes. We know that virtually the same ocean and 2 days apart, you can have a giant typhoon that's 1,000 kilometers across and a mini that's only 100 kilometers across. So there's always going to be kind of a random scatter. But what about the median size? Does that change with climate? We don't know. There's some theoretical evidence that it should get a little bit bigger as you warm the climate, but nobody's very confident of that. So your question is very timely because it addresses something we're all very worried about and working on, but I don't have a good answer for you yet. So, all right, I don't see any other questions there, but if anybody wants to ask any, oh, here comes one. What caused me to study hurricanes? Well, you know, in the original version of this presentation I showed you, I thought about telling you a little bit about my personal connection to hurricanes, and I said, nah, you know, that's too. But my very first trip to Maine ever, when I was 5 years old, was in the middle of a hurricane that hit Maine, and it wasn't one of the big ones, so I didn't show it to you in that. And we arrived at our rental cottage in Owl's Head, and the surf was immense, and I'd never seen anything like that. So I like to think that my entry into Maine in 1960, I don't know why my mother chose to drive up here in the middle of a hurricane. Maybe she didn't know what was happening, but the whole thing was very impressive. So there's a connection between me and hurricanes in Maine that goes way back. I'm sure there's a more complicated and complete answer to your question, but I'll leave it at that. Anybody have anything else they'd like to ask? Well, if not, let me ask Suzanne if she wants to take over. And
I see one more question here.
oh, okay. This is from Sheila. How receptive have policymakers been to these predictions? What kinds of tips do you have on communicating science to the public? Well, thank you for asking that. When I'm not talking about hurricanes, I do a lot of public lectures on climate, and I have some decade ago, I made a promise to myself that I would stop preaching just to the converted and go out and talk to the people who were resisting the evidence that we're putting ourselves at risk. So I went and talked to the Tea Party and so forth. And my colleagues have done the same thing. And I think things are slowly getting better. We still have an awful lot of denial, but if you look at the polls, politicians and people are slowly coming around to this. And you said, what kind of tips do you have? Well, I've learned something partly from my experience and partly by talking to congressmen and so forth, that you've got to understand that when an intelligent person says to you, look, I don't believe anything, I don't believe any of the evidence that you're showing me, it turns out almost always not to be really because they don't believe the evidence, but because they have been taught to fear the solution. And so it's very hard for climate scientists to give a climate talk and not talk about solutions. But on the other hand, talking about solutions is stepping out of one's comfort zone of one's a climate scientist. So I've had to give myself a crash course in energy policy and so forth, which is nice because I'm at MIT where there are a lot of people who do that. So if you can get people, so my tip is, if you can get people excited about the solutions, their resistance to the evidence usually collapses. And I've even had Republican senators tell me something very close to, look, Emanuel, I still don't buy your evidence, but I'm totally on board with the solution. Think about that for a minute. It's interesting, you know, what do I care about? Do I care that they believe me, or do I care that they do the right thing? Well, obviously, we have to care that they do the right thing. And so by getting them excited about the energy future, when I talk to Republicans, I talk about the importance of competing with the other countries of the world who are going to capture the $6 trillion energy market by going green. That gets them turned on, and I think that's the best hope for getting action on climate. That's just my personal experience. So from John, are you connected at all with the Maine Climate Council? Nice question. I've heard of it. No, I'm not. I have to tell you that I'm mostly still living in Massachusetts. It's only when they closed MIT down that my wife and I came up to Maine for a while. I would like to connect with the Maine Climate Council, so if you know a way for me to do that, I'm very receptive. And that comes from John via Linda, if I understand what you said correctly. Yeah.
All right.
Well, let me just say that it's been a real great pleasure talking with all of you, and wish I could do it in person, maybe next time.
Thank you so much. Yeah, this was super interesting, and we'll share the recording with others so the effect will be even larger. Oh, I see. Okay, the link for the Maine Climate Council.
Oh, thank you for that. I'm going to click on it before it disappears.
Yeah, maybe before you leave Maine to head back to Massachusetts, you can stop at the reserve and at least take a walk on our trails.
Yeah, I'd love to do that. I mean, it's one of the great joys of being in Maine is being able to walk trails. There are a lot around here too, but I'm game for sure.
All right. Thank you so much, and thanks everyone for joining. Hopefully we'll see you next month for the July lecture.
Okay.
Take care.